Flight 12's nightmare is over. 33 engines, 0 failures, a perfect ascent. But that's not the full story. 8 seconds into the landing burn, 8 engines just stopped. Not 1, not 2, 8. Officially, the flight was a success, but the telemetry raises a very different question. So which one do you trust, the press release or the data? Stay with me, because the answer changes everything. Let's go back 5 weeks. Flight 12. Because you cannot understand why Flight 13 matters without understanding what almost killed the program before it. During Flight 12, Super Heavy's engines started failing mid-ascent, a cascading failure with Raptors dropping out one after another during the climb. The investigation that followed wasn't a formality. It was the FAA and SpaceX engineers combing through telemetry line by line, trying to answer one question. Why did engines that were supposed to survive the harshest 10 minutes of the mission start dying before the hardest part even began? The answer they found was brutal in its simplicity. Heat. Severe thermal stress hit propulsion components during ascent. And on top of that, the engine alarm system was tuned wrong. Think of it like a smoke detector, so sensitive it goes off from toast. Except in this case, the alarms were shutting down engines that may have still been salvageable. 2 problems stacked on top of each other. A physical weakness and a software system that panicked at the wrong moments. So SpaceX did what SpaceX does. They went back into Booster 20, rebuilt the startup sequence, retuned the alarms, and reinforced the hardware. Then came July 10th, a full 33 engine static fire. 24 seconds of controlled fire on the ground, the longest test of its kind ever performed on a Super Heavy booster. It looked like the ghosts of Flight 12 had been exorcised. They hadn't. The ice that spoke first. July 24th. Fueling complete in under 38 minutes. Every light green. Then 1 to 2 seconds after ignition command, the abort trigger fired. 4 Raptor engines out of 33 refused to start cleanly. The cause traced back to something almost poetic in how mundane it was. Moisture had built up inside the oxygen turbopumps, likely a residue from the static fire days earlier, and when the cryogenic propellant hit that trapped moisture, it froze solid. Ice inside a rocket engine designed to survive temperatures colder than the surface of Pluto was enough to jam the machinery that keeps the whole system alive. One detail here should unsettle you. Losing 2 engines at ignition is an automatic abort condition, not a judgment call, not a maybe. The onboard computer sees 2 dead engines and immediately decides the mission has no safety margin left. 4 engines misbehaved that day. The system did exactly what it was built to do. It said no. SpaceX rolled the booster back, replaced engines, and pushed the launch to the following day. And this is where the story could have gone one of 2 ways. Either the fix worked, or the ghosts of Flight 12 had simply changed their disguise. July 24th, second attempt, same countdown, same 3-second ignition sequence. And this time, every single Raptor on Booster 20 lit. All 33, 0 failures, 0 aborts. The booster cleared the tower with a thrust-to-weight ratio of roughly 1.35, noticeably sharper than the 1.25 SpaceX was working with on version 1 of Starship years earlier. That number matters more than it sounds. A higher thrust-to-weight ratio means less time spent fighting gravity near the ground, which means less structural stress, which means a cleaner, faster climb. 58 seconds later, the vehicle hit max Q, the point of maximum aerodynamic pressure, the moment where a rocket is being squeezed hardest by the air around it. And this time, SpaceX did something they'd never done before on a Starship flight. They deliberately flew through a steeper, more aggressive ascent profile than any previous mission, putting extra stress on the vehicle on purpose. Why would anyone add stress to an already dangerous phase of flight? Because the heat shield tiles had load sensors embedded in them for the first time, recording exactly how much force the vehicle experienced. If a rocket can survive a harder max Q, and the data proves it, that unlocks the ability to carry more payload to orbit, because less energy gets wasted decelerating unnecessarily. This was a stress test wrapped inside an operational mission, and the vehicle passed it. At 2 minutes and 18 seconds, most of Super Heavy's engines shut down for stage separation. Then hot staging began. Picture 2 people mid-handoff of a heavy box. Nobody sets it down first. The receiving hands grip it, while the giving hands are still holding on, so the momentum never breaks. That's hot staging. Ship 40's Raptors ignited while still physically connected to the booster, and the transition happened without losing a fraction of built-up speed. 3 seconds later, Booster 20 executed its flip and lit its engines for the boost backburn, the maneuver that sends the empty booster back toward land. On Flight 12, this exact maneuver went sideways. The startup sequence was inconsistent. The flip came out nearly 90 degrees off target, and 5 engines refused to relight cleanly during the burn. This time, the flip was clean. The engines fired exactly as commanded. SpaceX had rewritten the startup sequence to tolerate more timing variability, and it worked. So let's pause and take stock, because this is the moment the video's title earns its claim. Every single engine that mattered during ascent, stage separation, and boost back performed exactly as designed. The nightmare that defined Flight 12, engines quitting when the mission needed the most, was gone. But rockets don't care about your narrative arc, and neither does gravity. The 5-engine mystery. At 6 minutes and 25 seconds, Booster 20 began its landing burn, the final maneuver that determines whether a 230-foot-tall steel tower comes down under control or comes down as debris. Here's how this burn is supposed to work. 13 engines ignite first, a mix of middle ring and inner ring engines working together to kill velocity fast. Once the vehicle stabilizes, 10 of those engines shut down in a symmetrical pattern, leaving just 3 inner ring engines to handle the final, most delicate seconds of the approach. That is not what happened. From the very start of the burn, only 10 engine gimbals activated. 3 engines in the middle ring, positioned in a specific pattern, 2 clustered together and 1 directly opposite them, simply never fired. Less than a second later, 2 more engines choked and shut down entirely. 1 from the middle ring, 1 from the inner ring. Then the remaining 3 middle ring engines cut out on their own. What Booster 20 was left with, for the most critical seconds of its return to Earth, was 5 engines instead of 13. Does 5 sound like a small shortfall to you? It shouldn't. At the moment the landing burn ignited, telemetry showed the booster was still screaming toward the ocean at over 2,000 kilometers per hour, roughly 7.5 kilometers above the water. That's faster than the cruising speed of a commercial jet, except this jet weighs hundreds of tons and is made of stainless steel. Killing that kind of velocity with 5 engines instead of 13 is like trying to stop a freight train with a third of its brakes disconnected. It can be done. It is not the plan. So what actually happened up there? 2 engines shutting down less than a second after ignition doesn't look like elegant engineering. It looks like something failed, fast, and the flight computer had to adapt in real time. The space community split into 2 camps over what happened next, and both sides have a point. Camp 1 says this was a genuine malfunction. Their evidence, the abrupt, uneven way engines dropped out, doesn't resemble a planned sequence. A deliberate shutdown would look clean, symmetrical, predictable. This looked like the vehicle was compensating for problems in real time, throwing extra thrust at working engines to make up for the ones that quit. Camp 2 says look closer at the pattern. The engines that failed to fire were sitting in symmetrical positions on the booster. In rocketry, when a booster wants to execute a specific balance or flip maneuver, engineers sometimes intentionally withhold engines on one side to create differential thrust, essentially steering by unevenness rather than symmetry. If SpaceX wanted Booster 20 to perform a very specific final maneuver before splashdown, deliberately idling certain engines is a legitimate way to do it. Which theory is correct? One detail tips the scale for most engineers watching the data. 2 of the 5 remaining engines lasted less than a second before shutting down too. A deliberate flight profile doesn't typically include engines that ignite and then immediately die. That pattern smells like hardware fighting back, not software making a graceful choice. The stakes of getting this wrong are real. SpaceX has already caught a super heavy booster with the launch tower's mechanical arms, nicknamed Mechazilla 3 times. But those catches happened with an earlier, simpler booster design, different engine layout, different grid fins. Version 3 introduces a completely new navigation system and works with a brand new launch pad. That kind of precision demands the vehicle behave exactly as commanded down to the second and the centimeter. A 5-engine scramble during the most delicate phase of flight is not the kind of behavior you want walking into a tower catch attempt. Booster 20 was never scheduled to attempt a catch on this flight. It splashed down in the ocean instead, hard, but within the designated safety zone, which means the mystery of what really happened during those 6 seconds remains open. SpaceX may release an official post-flight statement clarifying it. Until then, the data leaves room for genuine debate. The other half of the story, nobody's talking about. While the booster's ending gets messy, Ship 40 was writing a completely different story, and it deserves far more attention than it's getting. At 8 minutes, all 6 of Ship 40's engines shut down exactly on schedule. Compare that to Flight 12, where the ship lost one of its 3 vacuum-optimized Raptors about 40 seconds after separation. That failure didn't doom the mission last time. The ship still completed its trajectory on the remaining engines, but it was a red flag SpaceX needed to erase. This flight, it vanished completely. 0 anomalies in the ship's propulsion system from ignition to cutoff. Then came a test flight 12 never even attempted. At roughly 38 minutes into the mission, Ship 40 relit a single Raptor engine while in the vacuum of space, and the burn ran longer than any previous in-space relight SpaceX has attempted. That difference isn't cosmetic. Every future Starship mission beyond low Earth orbit, refueling flights, lunar landings, Mars transfers, depends on engines that can restart reliably after sitting in the cold vacuum of space for extended periods. An engine that only works once at launch is a firework. An engine that can shut down, coast, and relight on command is a spacecraft. This test just proved SpaceX has built the second kind. 16 minutes into the mission, something flew on Starship that had never flown before. 20 Starlink 5. 3 satellites, not dummy mass simulators, not placeholder weights bolted in to test the payload bay. Real, functional, next-generation satellites, deployed from a Starship for the first time in the program's history. This detail is easy to skim past, but it might be the most economically significant moment of the entire flight. Starlink currently relies on Falcon 9 to loft its satellites into orbit, batch after batch, mission after mission. The moment Starship takes over that job, SpaceX isn't just swapping one rocket for another. They're multiplying the size and capability of every satellite they can launch in a single flight, because Starship's payload bay dwarfs anything Falcon 9 can carry. This is the transition SpaceX has been building toward for years, and Flight 13 was the first real evidence it's about to happen. 6 of those 20 satellites carried something else, cameras aimed directly back at Ship 40's heat shield, streaming imagery down to engineers on the ground in real time. To give those cameras a clean reference point, several tiles on the ship's underside had been deliberately painted white, standing in for missing tiles so the cameras had a clear target to measure against. This is the kind of unglamorous, meticulous engineering that never makes headlines, but decides whether a spacecraft survives its next flight. And there's a very human reason it matters. A returning Starship's re-entry path crosses the continental United States before it reaches Texas. Knowing exactly how the heat shield is holding up before committing to that flight path is not optional. It's the difference between routine re-entry and a national incident. At 47 minutes, Ship 40 hit the upper atmosphere, and this is historically where Starship has either impressed everyone or terrified everyone. Plasma began wrapping around the hull as the ship pushed into thickening air, decelerating from orbital-class speeds down towards something a commercial airliner could survive. Here's the part most viewers don't fully grasp about re-entry, so let's make it simple. Getting to space is mostly about raw power, brute force engines pushing against gravity. Coming back is about surviving your own speed. Every bit of velocity the ship built up on the way up has to be shed on the way down, and that energy doesn't just disappear, it turns into heat, thousands of degrees of it, concentrated on a paper-thin layer of ceramic tiles standing between astronauts and incineration. This is why SpaceX considers the heat shield the single hardest engineering problem in the entire Starship program, harder than the engines, harder than the landing. At 1 hour and 2 minutes, the ship went transonic, crossing below the speed of sound. Less than 40 seconds later, it was fully subsonic, closing in on the Indian Ocean under control. 2 minutes later, the landing burn started. The ship snapped into its horizontal to vertical flip, a maneuver that looks almost physically wrong when you watch it. A 130-ton steel structure rotating in midair like it weighs nothing. Then it happened. Ship 40 didn't just land, it slid. Every previous Starship Ocean splashdown has ended one of 2 ways: a controlled landing followed by a deliberate tip-over and explosion, or an uncontrolled failure. This time, Ship 40 came down soft enough that it simply leaned over onto the water and stayed intact. No explosion, no fireball. Just a giant steel spacecraft floating on the ocean surface, still transmitting live video and telemetry back to mission control. For the first time in the program's history, cameras got an unobstructed close-up view of a heat shield that had just survived a full atmospheric re-entry. And what they saw told its own story. A handful of tiles missing near the engine skirt, some cracked tiles scattered across the surface. The tiles under the aft flaps were mostly gone, an area SpaceX already suspected would take the brunt of aerodynamic stress. But the hull underneath, the actual structural skin of the spacecraft, showed no damage at all. Let that sink in for a second. This ship flew through a deliberately harsher ascent profile than any Starship before it, survived re-entry heat that would vaporize most materials on Earth, and came out the other side with a scuffed heat shield and an intact spacecraft. That's not a rocket that almost worked. That's a rocket getting close to what full reusability actually looks like. What the engines really proved and what they didn't. So let's zoom back out and answer the question this video's title promises. Did SpaceX solve Flight 12's nightmare? For every phase that mattered most, ascent, stage separation, boost back, in-space relight, ship cutoff, the answer is unambiguously yes. 33 Raptors fired without a single failure through the hardest, most historically dangerous parts of the flight. The specific failure mode that doomed engines on Flight 12, thermal stress combined with an oversensitive alarm system, did not resurface anywhere in this mission's most critical phases. That is not a small win. That is the difference between a rocket program in crisis and a rocket program that's maturing. But the 5-engine landing burn is a reminder that solved and perfected are not the same word. Whatever caused those engines to misbehave, whether it was an actual hardware hiccup or an intentional maneuver executed in a way that looked messier than intended, it's a loose thread SpaceX cannot afford to leave hanging. Not with a tower catch attempt reportedly on the table for the very next flight, expected as soon as August. A booster catch requires trust in every single engine behaving exactly as commanded, at exactly the right moment, with zero room for a 5-engine scramble. Here's the twist most coverage of this flight missed entirely. The narrative going in was, will the engines survive? The real story coming out is that the engines mostly did, brilliantly, but the next challenge for SpaceX isn't engine reliability anymore. It's precision. Reliability gets you to space and back. Precision is what lets a robotic arm the size of a building catch a controlled explosion out of the sky. So where does this leave the program? Musk has already confirmed that barring any red flags in the post-flight data review, the next Starship flight will attempt a full tower catch of the ship itself, something SpaceX has never done. Booster catches are proven. A ship catch is an entirely different animal, different mass distribution, different re-entry profile, different final approach geometry. After that comes orbital refueling, the technology that turns Starship from an impressive rocket into the actual vehicle capable of reaching the moon and eventually Mars. And after that, the human-rated lunar lander variant, the version of Starship that's supposed to put astronauts back on the moon within roughly 2 years of this flight. Every one of those milestones depends on one thing being true, that Flight 13's engine performance wasn't a lucky outlier, but a genuine, repeatable fix. The next flight will answer that question for real, and if the landing burn anomaly happens again, in the exact same pattern, on the exact same engines, that's no longer a mystery. That's a pattern, and patterns are what turn almost solved into actually solved. The data spoke for itself today. Thanks for breaking it down with me. Like, share, comment, subscribe to The Space Brief. One more analysis is waiting on screen. I'm Adrian.